All right, so in the last part of our exploration, what you did is you put a point on the line and then you drew a secant, right? You drew a chord or a secant going from one point to another point, and you found the slope of that. And you found that as the slope got closer and closer, as the second point got closer and closer to the original one, that you ended up getting something that was very, very close to the original tangent line that you drew. All right, so you were doing a couple of things. One, when you put down two different points and found the slope between those 2 points, what you were finding was the average rate of change. All right, when we find the slope of the tangent at the point or the gradient at that point, we're finding an instantaneous rate of change. So it's the difference between what's happening over a period of time or over a range compared to what is happening at this instant and how quickly is it happening, right? So it's a rate of change because it's talking about how y changes every time x increases, right? Which is your slope, y over x. Okay, you'll notice that at some points the graph is steeper, like here at the beginning and here at the end, it's very, very steep. And then at other places the graph is less steep, right? That is going to show up when you do your derivative function, and you'll play around with that a little bit more in the next piece. One thing I want to show you is kind of why this works. We're going to zoom in a little bit, right? So I'm just going to go to Windows Zoom. We're going to zoom in, and I'm actually going to zoom in to that point that we were looking at, the 1, 1. All right, so we're going to zoom into that as close as we can, and I'm just going to keep zooming in. So this is 0.2468, so right about here is what we're looking at. So that's my center right there. We're just going to keep getting in closer and closer. What happens as we zoom in, right? And this is still the quadratic function. I've just zoomed in really, really close now, right? And you can see that it's going from 0.59 to 0.6 now, so it's not exactly 0.1, but regardless, this used to be part of my curve, and now it looks like a straight line, right? So that's the idea when we're talking about these derivatives. And in your exploration there, you were bringing the point closer and closer and closer. Basically what we were doing is zooming in so that we could get a point here and a point there. And when we're so close to the graph that it looks like a straight line, then the point between those two, the average rate of change between those 2 points, is approximately equal to the instantaneous rate of change at a specific point. All right, and so I'm going to zoom back out again. Let's see, zoom. We'll go step by step again. And what I want you to see again is this is just still the same part of the graph. And as we start to zoom out, you start to now again see your quadratic graph. And even that part that looks like it's curved, when we get close enough, it's going to look like a straight line. All right. Now, what we call this is a limit. And we don't have to work a lot with limits in this class, but we may need to have, you do need to have a basic idea. The other time that we used limits was when we were talking about asymptotes, right? Remember when we had an asymptote, the value got closer and closer and closer to a specific value without ever getting there. Well, this is similar. We're going to talk about the limit of those 2 points. In your exploration, you put 2 points down, and you started with 1, 1, and 2, 4. And then you brought that second point in so that it was closer to 1, 1, and you did 1.1 comma something, right? And so it was a little bit closer, and you kept bringing that point in closer and closer and closer. And really what we want to do is find the slope when those 2 points are almost on top of each other. That's the limit. We're finding the limit of the slope as those points get really, really close together. And so that's really the idea of a derivative, and that's how the derivative allows us to get the gradient of any curve at a particular point, the tangent at that point. Okay, now we're going to learn some patterns in the next part, and actually throughout the unit we'll find some other patterns, and we'll find some tricks and other things. But keep in mind that the real thing that's happening here is that we're taking 2 points and we're bringing them in together. The calculator can do that very quickly, right? That's why the calculator is nice, is because we just kind of punch it in the calculator and say, hey, find the slope here. And what it does is it does what you did in that last part 2 of the exploration. It makes 2 points, then it brings them closer, brings it closer, brings it closer, and keeps bringing them closer and closer until it's able to calculate what it feels is a correct slope for that specific point. All right. So hopefully that makes sense in viewing it this way, and we'll use that as we go on to the next couple pieces, next part of this exploration. All right.